Hey there, Josh here, and in this video, we'll explore how to work with time in the Plutus framework. Specifically, we'll learn how to use the concept of intervals to set deadlines for the smart contract to follow, and then we'll also learn a bit about the script contexts that are used in validator scripts. Now, before we get started, due to demand from the comments below, I made a Discord channel where like-minded developers can stop by and talk Plutus. The link is in the description below. Now, with that out of the way, let's get started. Before we talk about setting deadlines for our Plutus application, we need to understand the concept of intervals. Intervals, as the name suggests, is just a range between two numbers. In the case of Plutus, the range will be between two timestamps. So these ranges could be somewhere from -infinity to 2000, and 2000 to 3000, and 3000 to infinity. It doesn't really matter. Some use cases for using the intervals will be potentially setting a timeline that you have to wait before a user can redeem their ADA. Another use case is the opposite scenario where we set a specific deadline a user has to redeem their ADA before they get locked out. The use cases here are really limited by your imagination. Now, diving a little bit deeper into the intervals. In the previous video, we talked about a validator script. A validator script takes in three things: the datum, the redeemer, and the context. In the previous video, I didn't talk about the context, and we still won't talk too much about it, but we will dive into it a little bit. Our context is represented by the object script context, which you can see in the documentation. I've included a link to this page in the description below. If you look inside the script context object, it has two members: a script context transaction info and a script context purpose. If you look inside the context transaction info, you'll get the transaction info, which has the pending transaction informations for our validator script. So remember, this is the metadata of the transactions that we made to the on-chain code on the Plutus node. Now, if you look inside transaction info, there's a member that we are particularly interested in, which is relevant to this video, and that is the transaction info valid range. No surprise, it is the valid range of the transaction. And I'll show you how to set this up later. This member is represented by another object called the PostX time range. And if we look at that, we'll see that PostX time range is essentially a interval type of PostX time. So if we look at what PostX time is, it is essentially just a class or a new type that represents an integer. And the integer represents the number of milliseconds since the start of UTC time, which is 1970, January 1st. So essentially, PostX is just an integer. Now if we go back and we look at interval, we see that an interval essentially is an object that has two members, a from and a to, or you can think of it as the lower bound and the upper bound. And that's about as far as I'm going to dive into this to make this practical. But in the context of this video, our intervals are essentially a range of starting number and an end number, which represents time. So great, now we understand what an interval is. However, how do we interact with it? In the same documentation, if you scroll down, you'll see that there actually exists some helper functions over here that's available to use, like member, which is a function that takes in two parameters, the type A, which is an ordinal, but that basically means A is whatever variable that you give it. So in our example, A will always be the PostX time, which is an integer. Member takes in two parameters, the integer and an interval of integers, or interval of time, and it returns a Boolean. And what this function does is it checks whether the value that we give it is inside the interval, and that's it. And so there are many helpful functions to create intervals, such as interval, which takes in two parameters and returns an interval object. We also have helpful functions that will come in handy in this video, like from and to. From takes in a number and it returns an interval, and the interval is essentially the number you start at all the way to infinity. Likewise, to is from -infinity all the way to your number that you pass it. If we scroll down a couple bit more, we see other helper functions to help us compare intervals with each other. There's also helper functions like overlap and contains. Contains is particularly useful in this one, where we're given two intervals and we return a Boolean, where our second interval we give it, if it's all of our second variable, if the range of our second interval is completely encapsulated inside the range of our first interval, we return true. Otherwise, we return false. I won't go through all of these examples, but it's a pretty simple read, so I recommend just taking a peek. Now that we have the background information, let's get started on a simple live project. So in this video, we want to create a smart contract that has a sender and a receiver. A sender will just lock up the data that they want to give to the receiver, and that's it. We're not going to worry about authentication or anything else like that. So the twist here is that the sender will lock up the data that they want, and they'll also provide a deadline to the redeemer. All the receiver has to do is send a transaction to redeem the amount before the deadline has been hit. I also want to add another time limitation. In a made-up case, let's say we want to prevent other people from accessing the smart contract before a agreed upon time. And of course, we also want to make sure that the receiver can redeem their token before the deadline is specified. So this is our overall project. Now let's talk a bit about our implementation details. So remember, every Plutus smart contract has a on-chain and off-chain code. So our on-chain code, or our validator script, we need to define the datum and the redeemer that we'll be sending in. The datum would just be the timeline, which is represented in POSIX, which is just an integer. Remember, the ADA value itself is already stored in the transaction. In the case of the redeemer, we actually don't need anything, so we won't actually define one. Now for the off-chain code, we have the sender, who will be sending the datum. The sender will need to provide two things: the deadline they want their ADA to be redeemed, and then the amount of ADA they actually want to lock up. And as for the receiver, we also don't need to say anything, but of course in a real world application that would be extremely dangerous, because this would mean anyone can retrieve this locked up ADA. But with that detail aside, this is our implementation detail. Let's get started. Back on the Plutus playground, we should go to the starter demo file. The starter demo file is a starter contract. It's based off the game contract, and specifically what's most important for us, it just contains the bare minimum required for us to develop. Following along our API implementation that we just talked about, let's first define our datum and our redeemer. So for our datum, we talked about this, but we just want to use the POSIX time. And actually, to be able to use POSIX time, we actually have to import it. So specifically, POSIX time is part of the Ledger API. So what we could do is, over here in our import, we only explicitly imported two things: the address and the script context. So instead, we should just get rid of this, and now we can import everything. Now, it might not be the most efficient thing to do, but for the sake of learning, that's perfectly a-okay. Now back down. We don't really need a redeemer, so we can just get rid of all of this together. And then inside our validator script, our datum will just be the datum, but we want the variable. And the way to extract the member out of our myDatum object, we just say myDatum, and then we just call it time. Now, we don't have a redeemer, so in this instance, we just replace it with a parentheses set, which represents void, and we're not going to use that. And then we're going to use our script context, because if you recall from earlier on when we went through this, because our script context contains the metadata that tells us what our valid time range is. So we'll call this CTX. Right now, I'll just keep our validator script as is and go through some of the data that we'll be sending in. So our first case is we don't have a redeemer anymore. So as a result, we would just pass in void. Our datum types would be the same, and we just replace all that. As always, I'm not going to go over our validator script or our template Haskell code, everything that's defined here. It's essentially the same copy and paste we do in every single smart contract. The next thing we need to do is we need to define our schema. This is for our off-chain code, specifically our sender and our receiver. For our sender, like we talked about earlier, we're going to send in two things: the time, which is the POSIX time, and the ADA that they want to lock up. Our receiver doesn't need to provide anything, so we just give it the type void. Next, we have this contract function. It's already all implemented for us, so we don't need to do anything. But as a quick reminder, if you scroll down, contract is our endpoint, which is plugged into the Plutus playground and allows the user to configure and set up their endpoints to make the transactions. So we'll skip all that. But the important part of this function is that depending on the option the user chooses, it can either be a publish endpoint or a redeem endpoint. For the publish endpoint, we're going to repurpose this to be our sending API. So our I is our time. Now to quickly go over what this function does, inside this function, we're calling the endpoint of publish, which then would give us our param type that we specified, which is over here in our schema. And it's a tuple of POSIX time, which is really an integer, and the ADA value. This syntax over here is an anonymous function that basically extracts out these two values for us to use. Before we get into the other time constraint complications that I added to this video, let's just create a transaction to send our data over, which really consists of us creating our datum type, which we just provide the time value. And this constructs a myDatum object. And then with this object that we provide, we call the mustPayToTheScript function, which takes in the datum and the funds that we want to lock up, which then will create a transaction for us to submit. Very typical. Remember, every endpoint, we always need to create transactions and we always need to submit them. Now that we have our transaction, let's submit it. We call submit tx constraints, which is pretty straightforward. We just take the instance of our smart contract, which there already is an implemented helper function, so we just call it to get it, and then we provide a transaction. And that is all we need to do. Next, let's do the same for our redeem endpoint. So for our endpoint, we're not getting any values, so we just set void. In our do function, we just get our UTXOs. If we had a redeemer, we would create the redeemer type, but since we don't, we can just get rid of this. Now we just create our transaction and we want to collect everything from our unspent output, which is just whatever the sender has locked up. We will pass in the redeemer, which in this instance is void because we don't need to send anything. And then we simply just provide the transaction into our submit function, which is submit transaction constraint spending. We give it the starter instance, the list of UTXOs, and our transaction to do something with those UTXOs. Pretty straightforward. And at this point, if you just hit compile, we should have a working application. All right, compilation successful. So right now, if we try this contract, it will fail because we haven't defined our validator script. But you can easily fix that if you go back up and just return true. So the transactions would always succeed. We'll fix that later. Let's go back and implement our time constraints. We are making one constraint, and the constraint is that we don't want our sender to create a transaction before a certain time. Maybe a more practical example would be a developer create a smart contract that they set for a certain release date. They want to publish it live, but they want to make sure no one can access it. So to prevent anyone from doing that, they would set a hard-coded date so that any requests fail. And that's exactly what we'll do here. So to accomplish this, the first thing we need to do is we need to get the current time. We can do that by calling the current time function, which is a helper function that exists in Plutus framework. That function has a now member, which we extract. Now specifically is the POSIX time. I'm also adding some logging information. It helps in debugging and kind of seeing what we're working with. All right, so what I did here is I used loginfo, which is just a way for us to print into the console. And for the value we give it, we call printf. This $sign just means execute the line after the $sign first. Printf, for those who are unfamiliar, is just a very helpful function that takes in a string that also takes in these special parameters like %s, which represents a string. And these %s would automatically be replaced with a string variable that we provide, which in this instance would be these two values. So for the first value, we call the show function, which exists in Plutus, and what it does is it converts an object into a readable string. So the first parameter just provides us the current time in a string format. The second parameter provides the string version of open time, which is a function that we will implement to set a hard deadline. And so in open time, we just construct a POSIX time object and we just pass in 1. Feel free to play around with the numbers. We're great. Now that we have this, we can now log some time and we can go to our simulator and check and see what sort of variables types we're working with. But we're not done with the code yet. Now we need to actually use them. So we need to compare the dates. If the current time is less than our open time, that means we are trying to send a transaction before the time we decide the script is available. So in this case, we will just cancel the operation and do nothing, or just log a statement in this case. Otherwise, we would send our transaction. And that's all we need to do for our publish endpoint. Now let's update our redeem endpoint. However, before we do that, there will be a compilation error because we're using printf and the string parameter that hasn't been imported yet. So to fix that, we just go back to the top and we just do import prelude. Specifically, we just want the string. As for printf, we just import the text.printf module and explicitly import the printf function. Right, so we implemented our publish function. Now we want to implement our redeem function. This is for the receiver to take the money. Before, we just sent the constraint and everything was good. I've alluded to this a bit previously, but we need to provide our script context information about the time. We could just have easily created a redeemer object that had a POSIX time similar to our datum, but then we wouldn't have a chance to learn something. And for that something is, for all of the transactions that we create, it doesn't just have to be one script. It can actually be a list of multiple constraints that we provide. One constraint specifically being the time range that we are in. But of course, Plutus always have helper functions available to create these transactions. So what we need to do is create a list of transactions. And to do that, we do this. Okay, quickly, we just have this symbol which merges and combine our transactions together. We call prelude dot open close brackets because there are multiple instances of it imported, and we just want to refer to the one that Plutus implemented for us. Similar, and there must also exist multiple must validate in functions that we imported. So specifically, we want to call the function defined in our constraints module. So must validate in takes in a POSIX time range, and we're going to create a range by using the from helper function, which remember creates a range that starts from the time that we give it all the way to infinity. So what time do you want to give it? We want to give our current time. So just like we did with our publish endpoint, we get our current time from the current time helper function. And then we just pass that into our interval. And now by doing this, our script context now has a time range attached to it. Pretty cool, huh? So now with all of this, we are ready to write our validator script and make sure that our receiver is trying to create a transaction before the deadline that the datum provided. Let's get started. So back in our validator script, so we want to return true if the receiver makes a transaction before the deadline, otherwise this whole transaction fails. To accomplish this, we'll do So the first thing I did for helpful debugging purposes is I call this trace if false function. It's just a function that would print the string that we give it if the boolean that you give is false. Rocket science, I know. I defined a function called deadline reached, which essentially will just return true if the deadline has been reached and false otherwise. Now to do this, we're going to rely on some of the interval helper functions that we talked about earlier. Specifically, we want to use contains, and you want to see if from the deadline that we set and now, we don't have now implemented, but the high level idea is if now is contained inside the data that our user sent, that means we have reached the deadline. To actually get the time that we set in our script context, we need to pull it out from the transaction info valid range member. And to do that, we do this. Now this is hard to read and boggle my mind. So remember, this $sign means read everything from right to left. So this line right here is saying from our script context, grab the script context info member, and then from there, grab the transaction info valid range, which is the value that we set earlier in our receive endpoint. And now that we have this range, we would give that range into our contains function, which then would do the comparison that we talked about. Now this code isn't perfect yet because we want the validator script to pass if the deadline has not been reached. We rely on this helper function called not, which would inverse the boolean that we get. So if deadline has been reached, we would return false and we don't say anything. But if the deadline has not been reached, we would inverse that and that would be true. And then the receiver will receive their ADO. And that's it. And we hit compile. Yes, we need to import the brackets. So we go back up to prelude and we do a semi-group and everything inside of it. Hit compile. I've typed this in wrong. It's actually script context transaction info. And of course, we should wrap all of this inside parentheses so that we actually get a boolean that we pass back. All right, so many errors, but log info, capital I. All right, one more time. Okay. Clearly, I tried to simplify this a bit, but I was wrong. In our prelude, we also want to import show and everything inside of it, which would help us print our log info properly. Add a comma. And finally, we compile everything successfully. So for a very quick example, wallet 1 wants to send ADA to wallet 2. Let's say they don't really care about the deadline, so they just give a very large number. And they just give up 100,000 Lovelace or 1,000,000 Lovelace. As usual, we wait, wallet 2 redeems, and then we wait, and then we evaluate. Now if you look in the transaction, you see that we took the 1,000,000 Lovelace and that wallet 2 received the 1,000,000 Lovelace, which makes sense because we redeemed it before the deadline was hit. On a side note, if you also look up log and scroll down, you can see the print statements that we've been making. Now, to show that the inverse case is true, if we change our deadline to be 1, this function will fail. Let me scroll down. You can see that indeed, wallet 2 does not have the Lovelace. And if we further scroll down and look for our error, we look at error, we'll see that we have message redemption period hasn't been reached yet. And this is our trace if false method that we implemented. And of course, if we go back to change our hard-coded value for the sender to be a very large number, we would fail on our earlier state because they would not be able to make the transaction. So that's it. And so this is how you set up timelines and delays inside a Plutus smart contract. Now, as an extra plug, due to popular demands from the comments below, I decided to create a Discord channel where we can talk about Plutus development and hopefully share tips and tricks with each other. But besides that, please do the usual and like and subscribe to this video if you haven't. Otherwise, happy development and have a great day.